In this lecture, I'd like to review linear algebra, and I'd like to do it in such a way that I put a little bit of a new perspective on familiar ideas, and that perspective is going to help us understand what we care about when we are focusing on the numerical aspects of linear algebra. Let's review some of the notation that we use when we talk about matrices. It's easy to, get the number of rows and columns confused. So when I talk about an m by n matrix, I'm talking about a matrix with m rows and n columns. So m rows, 1, 2, all the way up to m rows, and n columns, so 1, 2, all the way up to n columns. And we'll use the notation a sub ij to denote the element of the matrix that is in row I and column j. And so, for example, if I say A2, 1, I'm talking about row 2 right here and column 1 right there. Now, we'll work with vectors a lot, and it's helpful to think of vectors as being matrices. And there's really two ways to do that. I can think of a vector as being a tall matrix with n rows and 1 column, and I would call that a column vector. Or I could think of a vector as being a wide matrix, so it has n columns and 1 row. And so, respectively, this is a column vector and a row vector. Now, most of the time, if I don't say what kind of vector I'm talking about, I'm really talking about a column vector. There's an operation we'll frequently apply to matrices called the transpose, and we'll denote it with this little t that we write as a superscript on the matrix. And what the transpose does is it switches the rows and the columns of the matrix. So if we start off with our m by n matrix A from the previous slide, then A transpose is the n by m matrix, where the first column of A transpose is the same as the first row of A, and the second column of A transpose is the same as the second row of A, etc. Now we will frequently transpose column vectors or row vectors, so it's worth pointing out specifically that if we transpose a column vector, then we'll get a row vector with the same entries. And if we transpose a row vector, then we get a column vector with the same entries. Sticking with fundamentals here, let's describe matrix vector multiplication. So I'd like to tell you how to multiply an m by n matrix A and an n by 1 vector x, a column vector, and the result will be an m by 1 vector, which is a column vector again, and that vector we will call ax. So how do we do this? Well, let's take the matrix A and let's take the vector x, and to get the first entry of ax, I'll take a11 multiplied by x1, a12 multiplied by x2, up to a1n multiplied by xn, and I'll add up all those products. So that'll give me the first component of the result ax. I'll do the same thing for the second row of A and the vector x. So a21 times x1, a22 times x2, all the way out to a2n times xn, and that will give me the second component of ax, etc. Now, another way to think of this is to write A in a block form. So I'm going to write A out in terms of its rows. So if A1 bar, this guy right here, is the first row of A, and A2 bar is the second row of A, etc., all the way out to AM bar, being the mth row of A, then the result is going to be this series of matrix products. Each one of these things is a scalar, a row vector times a column vector, and that will give the components of the result, AX. So this might be a slightly different way of writing a product that you haven't thought about before. I probably don't have to tell you that matrix vector multiplication is important. And so what I'd like to do is spend a moment to point out two viewpoints, two ways of thinking about matrix vector multiplication that will be useful in different contexts. So first, viewpoint number 1. And that viewpoint is that a matrix acts on vectors. And so I could think of a matrix as something which takes a column vector x in Rn, and it maps it to, or it outputs a column vector ax, which is in Rm. And in particular, A is a linear mapping, but it's a function that takes vectors in Rm to vectors in Rm. Okay, now viewpoint number 2 is flipped around. A vector acts on a matrix. So what do I mean by that? Well, think of x as being essentially a storage of all the coefficients. And I'm going to use these coefficients to take a linear combination of the columns of A. So if A1, A2, all the way up to AN denote the columns of A, then the product AX is the linear combination of those columns with coefficients x1, x2, etc. So in particular, this is a nice way of thinking about geometrically what's coming out of AX. What's coming out of AX is something which is a linear combination of the columns of A. We've talked about matrix vector multiplication. Now's a good time to review matrix multiplication. So I'll describe how to think about the product of an m by n matrix A with an n by L matrix B. We'll call the product AB, and the product AB is an m by L matrix. You'll notice selecting the m from the first matrix and the L from the second matrix. So how should we think about this? Well, we can think about it if we break down B into its columns. So if we take the columns of B, here B1, B2, all the way up to Bm, then the columns of AB are just the columns of B acted on by A. So the first column of AB is going to be A times B1. The second column of AB will be A times B2, etc. So this is kind of a nice way of thinking about matrix multiplication. In particular, one thing that's nice about it is it allows you to think about why certain matrix products don't make sense. So for example, if I wanted to take A times B1, I would need the matrix vector product AB1 to make sense. And if, in order for that to make sense, I need the width of A, in other words, the number of columns of A, to match up with the height of B1, so the number of rows of B1. And that tells me why I can only multiply an m by n matrix with a k by L matrix when those inner dimensions n and k are equal. Now I'll throw in just a random fact here, which will be useful for us down the road, and that is what happens when you transpose a product. So how does a product of matrices interact with the transpose? Well, if I take the transpose of a product, that is the reversed product of the transposes. That's a neat fact that'll not too hard to show and is something that will be very useful down the road. If I have a couple of column vectors, u in Rm and v in Rn, I can construct a couple of very special products using these column vectors. The first is the outer product, and the second is the inner product. So to construct the outer product, I'm going to take u and v, and I'm going to multiply u times v transpose. Now you'll note that u is a column vector, and v transpose is a row vector, and so the result will be an m by n matrix. This matrix is rank 1. It's kind of low content because I'm getting it from a couple of vectors, but the way I construct it is exactly how I would normally multiply matrices. I take the columns of v transpose, which are just scalars, v1, v2 through vn, and then I act on them by the vector u, which is just scaling u by each of those. So I get a matrix, m by n matrix, whose columns are u v1, u v2, up to u vn. Now, this outer product will work for any m and n. Now, you have to be a little careful because if you switch u and v, you will actually get a different outer product. You'll get the transpose. And how do I know that, or how do I figure that out? Well, if I switch u and v, that would give me vu transpose. And you'll notice that this is the same as u v transpose transposed by that reversal of the product rule that we saw on the previous slide. So if I reverse the order of the outer product, I get the transpose. Now finally, let's talk about the inner product. Now the inner product is one that is probably more familiar than the outer product. It's the same as the dot product, at least in the Euclidean sense. So how do I take an inner product? I'm going to take u and v. In this case, u and v have to be from the same dimension space. So m has to equal n, otherwise this does not make any sense. And to take the inner product, I take u transpose times v, which is just the sum of the products of all the components of these vectors. Now you'll notice here that since this is a scalar, if I were to reverse the order of u and v and take v transpose u instead, I would get the same result. It's transposed, but it's the same thing since it's just a scalar. There are two really important spaces associated with any matrix, and those spaces are the kernel and the range. Now, let's think about the kernel first. So in order to talk about the kernel, I would like to adopt the viewpoint number 1, where I'm thinking of a matrix A as a map from Rn to Rm. And so the kernel, or also called the null space of A, is going to be the set of vectors in the domain Rn that are mapped to 0, so that satisfy Ax equals 0. Here 0 is the 0 vector. This is a vector subspace of the domain Rn. And since it's a vector subspace, I can talk about its dimension. And the dimension of this kernel is called the nullity. Let's do an example of finding the kernel of a given matrix. We'll start out with this matrix A right here. And so in order to find the kernel of A, I need to look for solutions to this matrix equation right here with A times x equal to 0. Now, it doesn't change the solution space to do row operations on the matrix. And so I'm going to take the first row and add it to the second row, and I'm going to replace the second row with the result. And so instead of solving this equation here, I would like to solve this equation. A little easier. Now, you'll see that x3 is a free variable. It's unrestricted here because there are no pivots in that column. And so I can set x3 equal to anything I want. Let's set it equal to 1, and then let's back substitute to solve for the resulting x2 and x1. So if I set x3 equal to 1, I can back substitute, find that x2 must be minus 1, and then that x1 must be minus 2. And so what that does is it gives me a basis vector for the set of solutions. So the kernel consists of all multiples of that basis vector x, which is minus 2, minus 1, 1. So you can see that in general, finding the kernel amounts to solving some kind of a homogeneous linear system. It might be more than one-dimensional. It might be 10-dimensional, who knows? But it really just amounts to solving a homogeneous linear system. Let's talk about the other important space associated with a matrix. This one is the range. So again, let's adopt the viewpoint number 1, where I think of A as a map from Rn to Rm. Now, the range, or column space of A, is going to be a set of vectors in the codomain Rm. So a set of vectors B in this codomain right here, such that there's some x over in the domain that maps to the vector B in the codomain. So in other words, I can find some vector x such that Ax is equal to B. This is a vector subspace of the codomain Rm, and so therefore I can again talk about its dimension. And the dimension of the range is called the rank. It's always good to do an example. So let's look at the range of this matrix A right here. So in order to do this example, let's go back to viewpoint number 2. So I'm going to think of A as being something fixed, and I'm acting on A by a bunch of different vectors x and seeing what comes out. And so, well, what is viewpoint number 2? It says that if you have a product A times x, that's the same thing as a linear combination of the columns of A with the coefficients taken from the vector x. And so the range is going to be the set of all these linear combinations of the columns of A, where I choose different coefficients, x1, x2, x3. In other words, different vectors x to multiply A against. So I'm looking for what kind of a space I get out of all these possible linear combinations. And if you look at this for long enough, you can see that I'm never going to get anything but 0 out of the third component. And I'll get essentially anything I want out of the first two components by choosing different x1s, x2s, and x3s. And so I get a two-dimensional space, which is the set of vectors b1, b2, b3, where b3 is 0. And here we can see that since this is a two-dimensional space, the rank of the matrix A is 2. There's a big theorem in linear algebra that relates the range and the kernel. This is called the rank-nullity theorem. So let's let A be an m by n matrix. And the rank-nullity theorem says that the dimension of the domain, n, must be the sum of the dimension of the range, in other words, the rank, and the dimension of the kernel, in other words, the nullity. It's kind of an informal way I like to think about this. If I think about A as essentially taking the whole domain Rn and mapping it into Rm, it kills off some stuff, and some stuff survives in Rm. Now, the stuff that it kills off is the nullity. So you can think of A as killing off a whole bunch of stuff in the domain. That is measured by the nullity. On the other hand, a whole bunch of stuff survives and lives on in the codomain, and that size of that is measured by the rank. And the sum of those two sizes is the size of the whole domain. Let's look at some examples of consequences of the rank-nullity theorem. So we've already computed the rank and the nullity of one matrix, this matrix A here. And we saw that this matrix A had rank 2 and had nullity 1. And since the dimension of the domain here is 3, this A maps R3 to R3, we can see that 2 plus 1 is equal to 3. Okay, so rank nullity is verified. There are also kind of consequences that I suppose we could call examples. So let's say that A is a 2 by 3 matrix. That means it maps R3 to R2. Well, A must have rank less than or equal to 2. Can't have a rank bigger than 2. And so the nullity, by consequence of the rank nullity theorem, the nullity must be greater than or equal to 1, because the two of them must sum to 3. So that means that I have to have some kind of a kernel if I'm mapping R3 to R2. I can't squash all of R3 into R2 without killing off some vectors. Similarly, I have another consequence, which says that if I have an n by n matrix, a square matrix, mapping Rn to Rn. If it has 0 kernel, then its rank must be full, must have rank n. So it's surjective, it covers the whole codomain. Let's move on to our final review topic, and that is solving linear systems. So let's suppose that A is an m by n matrix as usual, and now let's pick a vector B in the codomain Rm. So a typical problem in linear algebra is to try to solve Ax equals b. And what that means is we'd like to try to find a vector in the domain, x in Rn, that maps to b in Rm when I apply the matrix A. I'd like to solve Ax equals b. So this is a system of m linear equations in n variables, and is probably the kind of problem that you have solved many times before. But let me remind you that conceptually speaking, there are really only 3 scenarios when solving a system of linear equations like this. These 3 scenarios, the 3 possibilities are: 1, there is a unique solution. So there's a single unique solution to Ax equals b. Scenario number 2 is there are no solutions. I cannot find any x's that map to b. And scenario number 3 is there are infinitely many solutions. I have a whole family of solutions x that map to b. So let's look at a couple of examples. So let's say I have a 3 by 2 matrix right here, and I would like to solve for x1 and x2 that map to the vector 1, 3, minus 2. You can verify that this has a unique solution, only one solution, a unique solution, x1 equals 1 and x2 equals minus 1. Another example. Let's take a 2 by 3 matrix, and I would like to solve for the vector, or a vector, x1, x2, x3 that maps to 2, 2. Now you'll find that I actually get a whole family of solutions here, and I parameterize them with a parameter t. And so I get this entire line of solutions in R3. For an example of the second possibility where there are no solutions, I challenge you to modify one of the examples I've already given. So you could take this second one right here and try changing a number in either the right-hand side or the matrix and see what happens. Okay, now I'd like to step back here and ask a question about systems of linear equations that you might not have thought about before, even if you've solved things like this a bunch. The question is this: if I were to give you a system Ax equals b, and I don't want you to do any computations with it, I just want you to look at it, can you tell me which of these 3 possibilities to expect? Unique, no solutions, or infinitely many solutions? Is there some kind of a guideline where I could just glance at it and say, oh, this is the typical situation, almost assuredly this is what's going to happen? So let's talk about that next. Before we discuss this heuristic or guideline that's going to tell us which of the 3 possibilities we might expect, I want to talk about tall matrices and wide matrices. So a tall matrix is one that is, tall, so it has more rows than it has columns. Now, here is the heuristic for a tall matrix. If A is tall, then we can expect, typically speaking, that Ax equals b has no solution. Well, why in the heck is that true? Let me give you a couple of perspectives here. If I have a tall matrix and I'm trying to satisfy Ax equals b, every row of A is going to give us an equation, which I can think of as a constraint. It's something that needs to be satisfied. Meanwhile, each column of A aligns with one of the variables, the freedom that we have to satisfy the constraints. And it is hard to satisfy more constraints than you have variables. Okay, how about another perspective? So in order to solve Ax equals b, we need b to be in the range of A. That is, the vector b, which is given, needs to be some linear combination of the columns of A. But the range of A consists of all linear combinations of n columns. So its dimension must be less than or equal to n. It could be less than if there's some linear dependence relationship among the columns. Meanwhile, since the matrix is tall, I know that n is less than or equal to m. So the range of A is some less than or equal to n dimensional space sitting inside Rm. It's some smaller space sitting inside the codomain. So if we just have some b and we need to find linear combinations of the columns of A that give b, well, we're going to have to be pretty lucky because b is just some random element of Rm, and it's probably not in the range of A. Let's look again at the first example from the previous slide, but this time I've tweaked a number. I took that -2 that was down here and I turned it into a 2. Now, let's think about what's happening here. I'm given a vector 1, 3, 2, which is in R3. And I am looking for a linear combination of these two columns that gives me that vector in R3. But there's two columns here, and if I take all possible linear combinations of these two columns, I'm going to get a two-dimensional space inside R3. And so that's a plane inside R3. Now, this guy B is just some random vector in R3. So I would have to get pretty darn lucky for that random vector to be in that plane. In the first example on the previous slide, I got lucky. In this example, I tweak one number, and I'm now not on the plane anymore. So this has no solution. Now for wide matrices. So a wide matrix is one that has more columns than rows. So in other words, it looks wide. Now, if A is wide, the heuristic here is that AX equals B will typically have infinitely many solutions. Again, let me explain why with a couple of different perspectives. So the first perspective is, as before, thinking of every row of A as an equation. Each row of A gives you some kind of a constraint. Meanwhile, each column of A aligns with a variable. So since the matrix is wide, you have fewer constraints or fewer equations than you have variables. And so in general, if you have fewer constraints than variables, you can satisfy those constraints, and you can do it in many possible ways, infinitely many ways in fact. Now for the second perspective. So to solve AX equals B, we need B to be in the range of A. Now, since n is greater than m, the range of A is probably all of Rm, because we're taking n vectors, the columns of A, and we're taking all possible linear combinations of them to try to fill up an m-dimensional space. Now, m is smaller than n, and so we have a pretty good chance of doing that, as long as there's not too much degeneracy or dependency among the columns of A. So B is probably in the range of A. Let's return to that second example from 2 slides ago, and let's tweak a number there. So in this case, I'm going to tweak this number right here. It was a 2 before. I'm going to make it a 1. Now, I invite you to solve this linear system. You'll find that there are infinitely many solutions yet again, just as there were for the case when this was a 2. And what that's showing us is that essentially, because I'm filling up all of R2 with linear combinations of these columns, no matter what I put over here, I'm going to be able to find infinitely many solutions to this system of linear equations. So now that you know about wide matrices and tall matrices, I've got a little screenplay for you, a real serious one, called Linear Algebra Meets Real Life. I'm going to act it out for you. I got this tall matrix A here. I need a solution to AX equals B, and I need it by tomorrow morning. Boss, I can't find any solutions. I don't care. Give me the best thing you got. People's lives are depending on it. The next day. Hey, Rob, I'm not sure why I'm asking you again, but now I got this wide matrix A. I need a solution to AX equals B, and I need it by tomorrow morning. Boss, I got infinitely many solutions this time. What am I supposed to do with all these solutions? Just give me a good one. People's lives are dependent on it. Life is often tall or wide, and we need to know how to deal with it.